Okay, so let's see. First of all, we have to say that, well, I just told you stops and moves are dependent on the application. Now here it says it's independent of the application. Well, this is kind of two sides of the same coin. Well, of course, the stops and moves can be somehow obtained from the raw data, yeah, by simply looking at the minimum time threshold. We see, for example, okay, this trajectory here stays in this region for a given amount of time, and in this region for a given amount of time, this region, blah 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 blah. And so looking just at the raw data and at the time aspect, of course, we can identify stops and moves independent of the application. But if we enrich those stops and moves that we can gain from the raw data without considering any semantics, if we enrich them with some specific application-specific semantics, we'll see that not all of the stops and moves, especially the stops, of course, that we identified are really, really important for us. Yeah, so this may be, for example, the region of the airport. So here, let's take this one here. This may be the region of the airport here. This may be a roundabout. This may be a traffic jam. This may be a hotel. This may be a crossroad. This may be some touristic spot, another touristic spot, whatever. So depending on the application, of course, some of these stops are interesting or not. So typically computing these stops and moves, especially the stops, can be done, of course, independently of the application. But then if we want to somehow interpret and analyze these stops, of course, then the application specific, the application dependent semantics come into play. And that's why it's two sides of the coin, so to say. Yeah. So don't get confused. I told you we are dependent on the application, and here we say it's independent of the application, meaning that the computation is typically, first of all, independent of the application, and then the enrichment of these stops. Are these stops really interesting to our application or not? That is, of course, dependent on the semantics, on the application. Okay, so before we talk about stops and move computation, first of all, one of the first approaches to enrich geometric patterns by semantics in order to get semantic patterns is from 08. So here the idea is just to work with geometry-based pattern mining and then enrich those patterns by some semantics. Yeah, so that's actually the same as I just sketched here. We just look at the raw data without any enrichment, any semantics, any application-dependent features. We just look at the trajectories, at the spatial and the temporal domain, and try to compute some patterns. And then afterwards, we enrich those patterns that we found, for example, the stops that we found, by some specific application dependent semantics or meanings. Yeah? And that is exactly the idea of Bogorny proposed in 08. So the point is here, very little semantics in most trajectory mining approaches so far. I mean, that's all about these geometry-based approaches. So the patterns that we get from these geometric-based approaches are, of course, purely geometrically, sometimes hard to interpret if we don't enrich them. So we try to take them and enrich those patterns with semantic information, what we just said. Yeah. And this is the pioneering work about semantic patterns. So this idea stimulated many other approaches on how to add semantics to geometric patterns, to geometric trajectory patterns. Yeah. So here's an example for some enrichment. Yeah, we have a flock pattern maybe here in that case. Yeah, and or an encounter. Yeah, maybe it's more an encounter here that a given number of trajectories cross this circular pattern here, which is called B. And if we just compute this encounter pattern here, we have no clue what B actually is. Yeah. So now we can try to add semantics to that. So we can, for example, look at, well, where did T1 start from? Well, T1 started from a hotel. And where did T1 went to? Well, T1 went to a cinema. And what did T3 did? Well, T3 also started from a hotel, but ended up in a restaurant. And T4 started somewhere, maybe at home, and ended up in another cinema. And T2 also started from somewhere, maybe at home, and ended up in a restaurant. Yeah. So this is an enrichment, and of course we can also look at this encounter region here and see, oh, maybe this is just the suburb center or whatever. Yeah, maybe it's the city center, but then it should be CC, of course. But anyway, maybe the suburb center or whatever. Yeah, so enriching the things that we find here, the encounter region, the stop, the beginning and the end of the trajectories. Maybe there is another flock pattern region or recurrence region or whatever, and we can try to look at the semantic enrichment and try to make some meaning out of those regions here, of course. Yeah? Which is not always very easy, of course, but you probably can imagine that it's doable. Yeah, and now finally to the stop and move computations. So this is one of the pioneering work here in 2007. So first of all, what is a stop? Well, we typically compute here first of all a candidate stop, which is a tuple where RC is the geometry of the candidate stop. So typically some kind of region, yeah, spatial feature type, yeah, region, a circle, a rectangle, whatever, yeah. And delta C here, the second part of the tuple, is a minimum time duration, yeah. So pretty much as I told you before here, so we're looking first of all for regions, yeah, spatial regions where trajectories remained in this spatial region for a given time slot, yeah, for a given time period. Yeah? And so we model those candidate stops as spatial regions where trajectories remained in for a given period of time. Yeah? So these are the two features of a candidate stop. So for example, it could be a hotel with maybe some kind of rectangular extent and 3 hours. That could be an example candidate for a stop. Yeah, and now we need, in addition, since okay, we could do that as we said here, independent of the application. But now the interestingness of the stop is, can we somehow make sense out of the stop? Meaning, is there some semantics that fit to those stops? Some of the stop candidates may be good candidates in terms of region and time duration, but it's useless for our application. So now we add an application A as a set of tuples again. Yeah. So again, candidate stops with non-overlapping geometries. Yeah, and relevant to the application. Yeah. So for example, in a tourist application, maybe we are interested in hotels and museums, and then we can map these candidate stops to hotels and museums, and those candidates that do not find a map with hotels and museums are neglected. Obviously, yeah, we can drop them because they are not interesting for our application. So now, how to compute a stop? Well, a stop of a trajectory with respect to an application is a tuple, yeah, with a spatial region and a start time and an end time, which is basically this delta C here, the minimum time, the time duration, yeah, such that the trajectory intersects this spatial region at all time slots between the start and the end time. And of course, that must be more than this. This delta C here. So delta C, that should be a LaTeX. So the backslash is missing here, obviously. Yeah, but anyway. Okay, so that's quite simple. It looks a little bit mathy, but it's pretty simple. Yeah. So that is a stop, and everything between stops or before stops, it's a move. Is a move. Yeah. So a move of t with respect to A is a maximal continuous subtrajectory of A between the starting point of t and the first stop of t, or between two consecutive stops of t, or between the last stop of t and the ending point of t. yeah, or the trajectory t itself if t has no stops, of course. Yeah, so here you see the trajectory t starting here, ending here, and here is a region that is interesting for our application, and seems that the trajectory is moving around in this area here more than delta c time slots. So this is one stop. The same here, second stop, the same here, third stop. So we have the stops here. All the time slots, or all the time slots that are in this one here, in this one here, and this one here are considered to be the corresponding stops. Yeah? And these parts here, the red parts here, are obviously the moves in this trajectory. Okay, sounds quite intuitive. Yeah? And this actually works quite well, and there's a cluster-based extension where the trajectories are clustered also based on speed. Yeah, so here we don't care about the speed. Here we just say, okay, if the trajectory is in a given region for a given amount of time, then it's a stop. Yeah, and that is basically dependent on this candidate stop list here from the application. So in this method here, we need to have an initial list of candidates, yeah, and then we can somehow compare our trajectories whether or not they stop here at those candidate stops or not. Yeah. This is somehow quite bothersome sometimes, because we have to come up with this application set here, with this candidate stops A here, set A here, that's why there's an extension by Palmer et al. In 2008 where they try to consider speed rather than, so they are application agnostic. First of all, they don't need to have these candidate application specific stop candidates. Yeah, they just look for speeds. Low speed is assumed to mean important place, and the other way around, of course. Yeah, and they propose to cluster the trajectories based on speed, and their algorithm is quite similar to this first one here, but clusters the trajectory points first and adds the semantics to the cluster. So it's again a kind of computation among the raw spatial temporal data, and afterwards adds the semantics to the cluster, like we did here in this semantic enrichment. So we don't compute any flock or any other Laube et al. Pattern, but we cluster the data here for speed, and then enrich those clusters with semantics. Yeah, so look for meanings to those regions here, actually. Yeah, that's all. Here you see a couple of further readings, basically the original work that we just glanced here. If you want to dig deeper, you're absolutely invited to do so.